the chat to interact with us, ask questions, comments. What we'll do at the end of the session, so the presentation is about 30 minutes, and at the end of the session, we'll take 15 minutes to answer your question. So you can note your questions here during the presentation. You can upvote comments from other participants, and that's the one we're going to prioritize when we come to this part. Okay. So I leave the floor to you, Elea and Louis, for the presentation. And thank you very much again. I'll stop sharing.
Yes, so let me share my screen. Can you see it now? Yeah, it seems so.
Yeah.
Okay, so let's deep dive in jinkō. So this is Elea's jinkō homepage, so you can see all the projects.
So with our jinkō subscription, it comes the Nova model library that you have a sneak peek here, with around 100 models of treatments and diseases. These models were either created by our teams or imported from the literature. In this case, we checked that we were able to reproduce the results that were shown in the associated papers with the information given or with the manual creation of the equations if necessary. So during this webinar, we will work on the inflammatory bowel disease model. And we will explore a model calibrated, simulated to answer a specific question on the model, such as which treatment has the greater impact on the biomarkers of interest. And doing so, we will illustrate the 3 core modules of jinkō: knowledge management, modeling and simulation, and analytics. So let's go to the inflammatory bowel disease project. So here's the homepage of the project. Classic organization in folders and with a create button where you can create the main objects in the platform. Each project comes with a README here, where you can find main information about the model. Let me just see it bigger. So today we will work on this model that was published by Rogers et al. In 2021, describing the interaction between the immune system, cytokines, and some biomarkers like the fecal calciprotein and the C-reactive protein here, that we will try to minimize during this webinar. So now we can have a look at the computational model associated with this. So let me go back here and switch to the computational model. You can see that let's just dismiss this warning message that won't be blocking, just for information purposes. And if you're curious about it, we can come back on those later. But here's the overview of the model edition interface of jinkō, where you can see a table listing all the different components present in the model.
So
just need to make sure everybody can see the screen. I think no sound.
So you can't hear me?
Maybe just to make sure to see the screen, there is a let's say a small on the left side of the window. You have like several icons, and I think you need to click on the 5th one to see the screen sharing.
Okay. So yeah, maybe Natalie, if you could do that. Yeah. So I think does anyone else has issues with the screen sharing? No, it seems to be fine. Okay, but maybe you can continue. Yes, Elea.
Yeah, so at this point, you might be wondering, how do I get my model in jinkō? So, of course, you could create it from scratch using this interface, but fortunately, we also support several formats to import your models to the platform and to ensure that jinkō can operate with other systems. So, for instance, you can import SBML models in the platform or SymBiology models. And pretty much the same for the export. We support the export to several formats, notably SBML with several versions that are available.
So on the right side here, you have information like an overview of the model with the numbers of number of compartments, of parameters, and different reactions and species.
So those metadata, they already give an overview of what a model looks like in jinkō. And actually, the core of a model in jinkō, there are the ODEs, so the ordinary differential equations, and the reactions. But actually, the reactions, they are really just some smart constructors around the most common kinetic laws. And they're here to ease the creation of ODEs in the end. So the system, it automatically takes care of the conversion. And you can take a look at all the ODEs of the model in the ODE system tab. So that gives you a different view of the model already. And if you're looking for an even more atomic view, you can go back to the computational model table of components and click on any component of the model to see like the specifics of that component.
One interesting thing is that you can have a look at the graph view here, where you can see how a specific components like CRP in the liver are affected by other components of the model and what they have an effect on. And you can navigate through this graph by selecting other components, for example. Going back to the general tab, you have information about how this specific component is defined, the formula associated to it. And since, for example, I'm not the one who created this model, I might be interested in knowing how, like, the specific reason why this formula was defined the way it is. And for this, I can have a look at the extract here, so the link, which links to the piece of literature that was used to create or associated with this component. So here, associated with this component upon creation by the QSP modeler. So it's really helpful to track all the information and how everything is linked together, and you can really go back to the original piece of information that was associated with each component. So let's go back to the computational model. So here we have the CRP concentration in the liver, amount in the liver, but let's say we would be more interested in having the concentration instead of the amount. So we can create a component for this. So let's create this concentration of CRP in the liver, which would be, so we can take the amount and the volume of the liver, which is in picomole per milliliter.
So you might have noticed the small warning signs that popped up while Elea was navigating the computational model table. So those are some diagnostics that we automatically run to ease the model creation and the debug of the model. So there are several levels of severity for those diagnostics. And for instance, like the error diagnostics that would be in red will completely prevent the model from being simulated. And so one of those error diagnostics, they are the unit checking diagnostics. So we automatically check that all the model components units are consistent. And it's a feature that is in general really appreciated by the modelers that use jinkō, as it prevents many mistakes like ill-defined formulas, for instance.
So here it prevents me from forgetting the volume, for example. Yep. So now that we are satisfied with the model structure, we can move on to calibrating the model. And for this, I can have a look at the different components that were identified as having a need to be calibrated during model development, which are these two parameters.
So what Elea just used is the tags, which are meant to characterize the model components. So it can either be based on, let's say, a biological phenomenon that the component is involved in, but it can also be a user-defined operational characteristic of the component. So for instance, specifying that you want to calibrate it, or this is something that should vary across the protocol arms of a trial simulation. So in a word, they are really used to ease the filtering and search of model components in our model edition module.
Thank you, Louis. And we can now move on to the calibration with click on the calibrate button. Quite intuitive. And then welcome to the calibration interface of jinkō. So calibration is a process to estimate parameters values to fit a specific behavior, such as clinical data. We will go through this process step by step, and starting with the definition of this target behavior. So here you have the computational model. And here I have a data table of observed value for CRP in blood at different time points that can be used as the target behavior for the algorithm.
So the calibration algorithm, it will try to converge to some parameter values that minimize the fitness function, which can typically be seen as a distance between the target data that Elea just showed and the simulated data. And one of the, let's say, key features of our calibration module is that this fitness function, you don't have to define it yourself. It's automatically computed from the data in the table. Basically, each line of that table will, which corresponds to an observed value at a given time, will contribute to building the overall fitness function.
So we can now move on to the calibration option, where the first thing to select is the parameters that we want to calibrate. So we can find them again with the calibrate tag, and let's select both. And so the calibration, the parameters to calibrate are associated, have by default some distribution associated to them based on the value that was in the computational model, and a standard deviation of 10% around this value.
So the calibration approach that we use in jinkō is called mean patient calibration. So this means that we try to find a single set of parameters, so a single set of values for those two parameters that optimizes the fitness function. And so the algorithm that we use for that is called CMAES, which is an evolutionary iterative algorithm. And so at each iteration of the algorithm, we sample a new population based on the individuals from the previous iteration and the value of their fitness function. So There are several ways to configure this algorithm in jinkō. So that includes, of course, the size of the population that is drawn at each iteration and the number of iterations that we run. So the users, they don't necessarily have to bother with defining those values, since we automatically compute some default ones based on the number of parameters to calibrate. So in our case, there are 2 parameters. But here, for the purpose of the demonstration, we can only run a few iterations, like for instance, 10 iterations, and see what this gives. So we can now we're now ready to launch the calibration. So we just have to click on the button, and once you do so, you get a small recap of basically what's going to happen and like the size of the computation. So that's 10 iterations with a population of 6 patients at each iteration. So that's the default value computed by the system. So once we're happy with that, we can launch it. And once the calibration has started, should be anytime soon.
Yes.
So you don't have to wait for the calibration to finish to see the first results. So you get a first plot that shows you how the fitness function evolves versus the number of iterations. So that gives you a sense of whether the calibration has converged yet or not. So in our case, with this small number of iterations, it doesn't look like it has converged yet. So it probably means that we should run more iterations. So that you can do simply by going back to the calibration options and increase the number of iterations. And it also illustrates like a nice feature that you don't have to recreate the full calibration object. You can simply modify it, and it will create a new version of that object. And then you can later browse through the different versions of the items. So this behavior, it's not specific to the calibration. It's actually available on any item of the platform. So that includes the computational model, but also any trial simulation input. So now that we've added more iteration, we can relaunch the calibration and see how it goes.
So while the calibration is running, we can have a look at the other type of graph that are available to follow the process, the algorithm progressing, and notably, for example, the evolution of of the value of the parameters that we are trying to calibrate. So for example, here the degradation rate. And you can see here that one particular value seems to be optimizing the fitness score here. So which means that first it has a good, it's while it's converging, and also that this parameter seems to be identifiable, which is a good thing. And switching between the two, yeah. We also have a look. We can also have a look at the individual patients, which are which automatically shows you the best patient. So the best patient being the patient with the parameter values that are closest to the data that was used, that is used as the target for the algorithm. So you can see the data here is the little crosses there. And you can already see that this patient has a good score and is fitting not so badly the data. So you can have a look. This doesn't seem to progress yet, but I'm afraid maybe it's because we're sharing the screen, and that's why it's little bit slow, but
I think we can move on with updating the model directly with the best
sure.
patient.
So one interesting thing is that when you're satisfied with the best patient values here, you can directly update the computational model using this best values there. This is a recap of the changes that will happen. And we can have a look at how the computational model was changed. And again, we can have a look at a different version.
So you can see that a new version of the model has been created with the new parameter values. And in particular, that this new version is also associated with a link to the calibration, so that allows to ensure traceability to the parameter values. So someone who doesn't know the model can know where the calibrated parameter value comes from. So that's so quite a nice feature of our platform in terms of traceability.
Yes, and the link of the calibration is also associated with the different parameters there. So now that the model is calibrated, we can launch a larger simulation to answer our question of interest. For instance, which of the implemented treatments has the higher impact on the C-reactive protein and the fecal calci protein? So for this, we just click on Solve Model here. And we have the simulation interface that is very similar to the calibration one.
So just like the calibration, the trial is fully configurable. So starting with the outputs of the trial. So what do you want to visualize once the simulation is complete? So here you can select an already existing set of outputs, or you can create a new one. So here for the demonstration, we'll just select an existing one. And what you can see is that you can either directly output the quantities as time series, or you can extract a specific value from the time series. So for instance, you can extract the last value or the average over a given period of time.
And next thing that you can configure is the virtual population. So you can see a virtual population as a set of virtual patients, each of them defined as a vector of specific biomarkers values. Here we have created a virtual population based on the paper by Rogers et al. Corresponding to Crohn's disease. But again, you could have created this from the CM directly by defining the target distribution of the parameters of interest and the correlation between these different parameters. We can now move on to the protocols. Protocols are particularly useful to test different scenarios, especially associated to treatments, for example. Here we will compare the effect of the 4 treatments that are implemented in the model. So an anti-IL-6, brazikumab, which is an anti-IL-23, infliximab, which is an anti-TNF-alpha, and ustekinumab, which is an anti-IL-12. And using this process, you can control which treatment is given, but also the start and stop time of the administration, and basically any other treatment parameterization that would be implemented in the computational model, such as the dosing, the frequency, or any other parameters like this, for example. Here again, I used a predefined protocol design, but you can create your own from scratch. from the model directly.
And so the idea is that each virtual patient that you define in the virtual population will be simulating on all the 5 protocol arms. So then each treated patient can be compared with the exact same patient without treatment and with a different treatment. So in a sense, each patient is its own control. So once we have finished configuring the trial, the last thing that you want to specify is the duration of the trial. So how long you want to simulate your model for. So we can simulate for 50 days, for instance.
Yes, and you can also control the observation frequency, so we can go for maybe every hour, let's say.
And once you're happy with the settings, you can launch the trial simulation. So just like for the calibration, you get a small recap of the computation that you're about to start. And so you can launch it. So that's the, let's say, monitoring page of a trial simulation. So you get a sense of how long it takes to run your trial and how long you have left until your trial is finished. So you don't have, just like for the calibration, you don't have to wait for the trial to complete to see the first results, as you get like some individual patients' results directly in the trial monitoring page.
And you can navigate, you can already navigate through the different virtual patients and have a look at how they behave, select different arms if needed.
So internally, the OD solver that we use for simulating the model is called Sundials, and it's really a state-of-the-art OD solver. So this allows to get fast results and this is combined with out-of-the-box parallelization capabilities. So that means that the platform scales automatically depending on the computational load, and that's regardless of your workstation capabilities. So what you might have noticed is that at the beginning of the simulation, it would tell you that you have, let's say, 10 minutes left until the end of the simulation. So that's because the farm hasn't scaled yet. But then as the trial progresses, you have to wait less and less time. And actually, it took maybe 1 or 2 minutes to complete the simulation, which is far from the 10 minutes that were initially anticipated. And to give a sense of the computational power of the platform, we recently managed to simulate a population of 1.5 million patients in about 45 minutes. And that was using about 4,000 processors.
So as soon as the trial is finished like this, you can visualize the results. And to do so, we need to create a trial visualization that we will just simply call results, for example. And we will now have access to the results at population level. So for example, here are the different specific values of the biomarkers at 20 days across the different arms. To see better, I can just put it in log scale. And to answer our question of interest, which was which treatment would be the most efficient to reduce, for example, the concentration of CRP in blood. So you have the not treated arm here. It seems that after 20 days of treatments, the most efficient one is the anti-IL-6 here. And for the FCP, for example, we can also have the log transform. And even if the effect is not as clear for the RCP, but you can see this time it's more the infliximab who seems to be best for reducing fecal calciprotein. You can also have a look at the time series, which are automatically computed, and they give you the evolution of the specific variables here at the population level, where you have in solid line the median evolution of the population. Then you have the 25 and 75% quartiles, and the 2.5% and the 97.5% quartiles automatically computed, which is nice to give you an idea of the variability across the different across the virtual population.
So there are many other visualization options that are available. For instance, you can filter the population, apply filters to the population, or group the different patients according to one of the population characteristics. There are also some automatically computed visualization, including some sensitivity analysis to see the most impactful descriptors on the outputs of the model. Or you also have the survival analysis, provided that you have some notion of time to progression defined in the model. But for some users, the visualization in jinkō or even the interface could be considered too restrictive. Yet those users, they would like to benefit from the computational power of the platform. And that's why we recently decided to expose a programming interface, meaning that you can directly interact with the platform programmatically. And each action, so each programmatic action will be automatically reflected in the interface. So that means that you can create items like trial simulations, protocol arms, calibration out of the platform. But you can also download the results of trial simulations to analyze them using different softwares.
So that's it for the overview of jinkō's current capabilities. There are many more functionalities to discover, of course, and we're currently working on new features to make jinkō experience as smooth as possible. So we hope this made you want to use it, and we will now answer your question. Just before, maybe Tanguy, you want to have a closing words?
Yeah, thanks a lot, Elea and Louis, for the great presentation. Indeed, there's much more to come. We couldn't cover everything today, but we'll be sure to keep you updated on what's coming into jinkō. Maybe to that note, while we still have 5 minutes left, I've just displayed a small survey here. Just while we answer your questions. If you have any, I see that there's not a lot, but I have some. Unless anybody wants to put something. But you definitely give us your opinion on the topics that will be of interest for you on the next webinar. And for the next 5 minutes, we can answer a few questions. So I start with a question while other participants add some in the chat if you have any. Maybe for you, Elea, could you tell us a bit more about how many models we currently have in our model library and the type of verticals we specialize in?
Yes, so we have around 100 models currently in the NOVA library. There's a little bit more than 30 centered around diseases. So around oncology, for example, non-small cell lung cancer or acute myeloid leukemia. And we also have a treatment library with more than 15 treatments implemented, and a few templates of different treatments, like a PBPK model, for example.
Okay, thank you. I can answer the question. So see, we have a question from Julie, so I can answer that. Are you planning to integrate AI features to help with data extraction, model construction? Yes, we definitely are. So we are planning, actually already implementing AI tool to extract, to ease the extraction of data from the literature. So for example, to transform the rendering of a LaTeX equation in actual editable LaTeX. We also can extract images of table in actual data table. And regarding the model construction, so yes, we also, there's going to be more R&D topic in 2025, but we're quite advanced on that. We're working on from references, easing the construction of equation to integrate into them. I think, thank you, Osman, for your question might be more for you, Elea.
Sure.
Do you have any? Yep.
So do we have any cell or gene therapy related models in our repository? So currently no, but it's something that we've been investigating and that we're currently working on to try to identify several models related to this. So it might be coming soon. Depending, of course, the models that we integrate in the library are based both on interests that we see from the community, let's say, and interest from our diverse clients. In any case, what we try to do is to have literature review to find the different models that might be of interest, and we evaluate them and select those that seem more pertinent and have the most chance of being implemented. So there's a process of qualification, different models. So if you're specifically interested for this, maybe we can also continue this this qualification process around gene therapy.
Okay, thank you, Elea. I see that there's not any other questions. Actually, we're on the end of the scheduled time. So we're very mindful of your day. Actually, maybe one last question from Didier. How do you manage non-identifiability? Do you have some plots? Maybe that's for you.
Yeah, so identifiability of the parameters has typically been a recent example of how we leverage the programmatic interface to get results from jinkō. So we have implemented a notebook to explore identifiability and uncertainty quantification around the results of a calibration. So that's something that's directly available for anyone with an access to the platform, as we have open sourced the code to explore that. So in the longer term, that might be something that will be directly available in the platform. But in the short term, it's something that you can explore using the programmatic interface of jinkō.
Okay. Thanks, everyone. Is there any other question before we wrap up? Seems to be good. All right. Okay, then thanks a lot, everyone, for your participation. It was very great sharing all of our latest innovation with you. You can always contact us, so it's pretty easy. Contact at nova@silico.ai. You can also request actually your free demo on the website, so www.jinkō.ai, and find useful resources at Nova. And we make sure to keep you posted on the next webinars coming. Thanks a lot. Have a great day, and we hope to see you soon.
Bye.
Bye-bye.